While the octet rule generally holds, and most atoms involved in bonding are going to have 8 electrons associated with them, there are some exceptions to that rule. And there are 3 main types. The first of which is in situations where you have an odd number of electrons. So this kind of situation comes up most commonly in molecules that have an even number of nitrogen atoms. So for an example, we'll draw the Lewis structure for nitrogen dioxide. Nitrogen has 5 valence electrons, and each of the oxygens will have 6. So there's a total of 17 valence shell electrons that we need to deal with when we draw this molecule. So we follow the standard rules for drawing Lewis structures. This structure clearly doesn't satisfy the octet rule for nitrogen. Nitrogen only has access to 5 electrons, so we need to make some double bonds to try to fix that. So when we draw a double bond, we end up with a situation where nitrogen now has 7 electrons, which is close to a full octet but not quite there. And if we went and made a triple bond, or maybe a double bond on the other side, we would end up with 9 electrons around that nitrogen, which is too many now. So there's no good way to give the nitrogen 8 electrons in this example. And we're not going to go into it now, but in a later video we'll talk about the idea of resonance, and we'll talk about how the structure for NO2 that I've drawn is not quite correct, but it's very close. And we'll eventually see that these two diagrams, that these two Lewis structures, while not exactly correct, are very, very close to correct and exist in what's known as resonance with one another. The second exception to the octet rule is when you have not enough valence electrons. So sometimes you can run into situations where you simply just don't have enough electrons to make an octet. It's not that you have an odd number that it's difficult to make the octet work, it's that you've just physically run out of electrons. And this situation is most common with boron and beryllium. And we use the example of Bf3. So boron provides 3 valence electrons, and the fluorines each provide 7. And we end up with a total of 24 valence shell electrons, and we go through the standard method of building a Lewis structure. And we have used up 24 electrons. We used 6 around each of the fluorines, and we used a total of 6 for the 3 bonds. And we've run out of electrons. We can't finish boron's octet. And you can't fix it by making double bonds either, because in this situation, if you make a double bond, it would give fluorine a positive formal charge, which is just absolutely unacceptable. This kind of works. You've fixed boron's octet, but at what cost? You've given fluorine a positive charge, and fluorine being the most electronegative element, that's just totally unacceptable. So the only good Lewis structure for Bf3 does not satisfy the octet for boron because you run out of electrons. The most common exception to the octet rule is when you have too many electrons. And this is the largest class of exception. It happens all the time with elements that are in the 3rd row of the periodic table or lower. And we'll give an example here with SF6. So SF6 has 48 valence shell electrons, and we follow the general rules for making a Lewis structure. We put the least electronegative thing in the middle, and we draw bonds connecting that central atom to the more electronegative atoms. And when you use up all the electrons, you end up with a situation where the central sulfur has 12 electrons around it, which is way more than an octet. And there's really no other way to arrange the atoms. Even if you joined some of the fluorine atoms into a chain, it wouldn't provide you with a good Lewis structure because the formal charge for fluorine would be incorrect. So this is really the only thing you can do. And the reason this can happen is because atoms that are in the third row and further down are just big enough that you can jam more stuff around them. And the smaller atoms, so anything in the second row or first row, are just too small. So if you wanted to have something like hydrogen with a bunch of atoms around it, even disregarding the fact that it doesn't have the orbitals required to hold those electrons, you just couldn't put them around it because hydrogen is so tiny.